Okay, I'm going to give you a talk about how to map caves. I've been caving for 30 plus years, a bit of an obsessive hobby, mixed with geekery, of course. And we should probably start with the obvious question of kind of why. If you're exploring anywhere that's kind of unknown, then obviously maps are extremely useful. And so you seek out the best information in order to kind of get get to where you want to go, see the things you want to see. But what if nobody's made a map? Then you're going into the unknown. And so you need to kind of map as you go so that you can then record what you found, find your way in future, provide information to other people. And actually some of the cave maps I've produced of caves that we've discovered in northern Spain are now used by the cave rescue services there, so that when they have youth groups who go in to look at the kind of amazing sites that we've discovered in some of the caves, and they don't come out again at the time they were supposed to, the rescue team have got a kind of map to plan their kind of search and rescue operations. So lots of reasons for having maps. But some of you may not be familiar with kind of like the sorts of things we're mapping, so I thought we'd start with a kind of like why go caving in the first place, and here's a kind of little taster of some of the stuff that makes caves, for me, fascinating. Out my slideshow, just 1 second. So some examples there of the kind of unique, fascinating underground environments that we make maps of and explore. So we can't do kind of what you might do for mapping a landscape, of kind of get some satellite imagery and do some kind of surveys from the top of some mountains where you can see a large area of the landscape. You've got to physically go where the cave goes. So what do we actually measure when we're making a map? And the basic techniques, and they've been kind of really unchanged in terms of what we're measuring since cave exploration, kind of like in the early 19th century onwards, is we measure essentially a vector through the cave, point to point. So we pick a convenient rock that gives us a kind of good onward sight, and we measure a three-dimensional vector, so distance, compass bearing, and kind of declination, so how horizontal, what the slope is, between those 2 points. And you just carry on doing that through the cave to get your basic where does the cave go information. That's kind of like the backbone skeleton of a cave survey. But it's obviously also really useful to kind of measure some kind of indication of kind of how big is the place. So at each station we also measure the left, right and up, down dimensions to the walls. And that gives us a kind of passage dimension, sort of cross section if you like, through each of those stations. So we go through the cave, making these measurements, and that gives us a backbone much like this, and I will switch to show you an actual live. So this is a piece of actually the Wookiee Hole cave system, and this is a three-dimensional plot, and with that left, right, up, down data that we've measured at each station, we can actually put some kind of like solid flesh on the model. So there we've got a piece of cave passage as our kind of basic model going through the cave. We'll come back to the model viewer in a minute. Because we need to look at how do we make these measurements. And you can actually see in this photograph they're using a fiberglass or a fiber-on tape measure. This is the kind of technique that we used pre-digital tech. So a tape measure, a sighting compass and clinometer. So in this device you see in the middle, the bottom dial is a compass, so when it's held horizontally, it's a sighting compass. You look through a kind of window to read the scale, and so you can measure bearings accurate to about kind of half a degree, and then the clinometer works by measuring essentially which way's down, so you know how steep, and you sight from station to station. And we used to write the numbers down on waterproof paper. These kind of type of propelling pencils are really useful because it is a real pain if you break your pencil nib on a kind of 12-hour caving trip, and so rather than kind of have spare pencils is good, but I found the propelling pencils were actually really dependable. Still carry a spare, because if you drop your pencil and it drops down between some gaps in some rocks, then you're a bit stuffed. And we would sketch a kind of drawing of the kind of passage detail at the same time as we went along. So we need to talk a bit about working conditions. I've shown you some pictures of some of the kind of amazing stuff that we go underground to go and see, but it's not all like that. And this will give you a bit of a taste of what the actual kind of working conditions that we have to survey through are really like.
Bag there if you want it.
Yeah, it'd be handy.
Just keep the water a little bit.
Just put the bag in the water and you can kind of lean on it.
When you're exploring, sometimes you have to excavate it big enough to fit through in the first place.
I think I can. There we are, that's probably better.
It's unpleasant.
I wouldn't like to have to reverse this.
No.
I shan't be coming back.
No.
That's a short back. I've done it.
Once experienced, never forgotten.
I've done it enough times. It's a pity it's not a foot wide, eh? Good job it's not full of friggin' water as well.
Oh, God.
It would be a bit unpleasant.
Well, I'm just going to have a look round now and see.
The water's definitely salty.
Oh, I love the caves.
And I'll wait here.
Yeah.
And then it's up.
So as you can see, all good, clean fun, great for taking the kids. And so as you can imagine, it poses some challenges. People who have never been caving and are thinking like, well, how are you going to build a map? Well, kind of take down a laser theodolite and kind of just build a point cloud. And people do that, but in very selective caves where you can carry it in on a backpack and put it down and it's not going to get wet. And you gather an immense amount of data, but it's very difficult to make a map from a kind of multi-million point cloud of a room. So to measure the whole thing, we still do that traditional point-to-point. The old equipment has the major advantage that it's almost indestructible. There are occasions when to read the tape measure you have to lick the mud off first, because it's the only way. You can't wipe it off because you're covered in mud as well, so kind of like licking the tape measure is a known thing. And if you get mud on the sighting compass, then that can kind of ruin them, so that's the thing you try and keep dry at all costs. But the downside, apart from the tape measure licking, is that to read a sighting compass, you have to get your head down and look along the line of sight that you're trying to measure in the cave. And you can imagine in some of those really confined spaces, that's really difficult to do. So our solution was obviously to go digital. And a Swiss caver called Beat Hieb designed a conversion for some of the Leica laser measures. This one was the most popular one because the actual laser measure was kind of semi-waterproof, so you didn't need to kind of look after it quite so carefully in the cave. But what you can see on the screen here, you can't see the distance because it's not actually measuring at the moment, but you can see it's measuring a compass and it's measuring a inclination. And so what is inside there, we'll look at in a minute. And the data, with some research into kind of blunders in cave surveying found that in somebody licking and then measuring, reading a tape measure which is covered in mud, shouting out the numbers to somebody else who's writing them down on a muddy notepad with muddy hands, and then taking it out of the cave and transcribing those numbers into a computer. There's so many opportunities for blunder that you get an error in maybe as little as 1 in 10 or less readings. This modern technology enabled us to use Bluetooth to send the data from the measuring device, which was an all-in-one, one zap and you've got your vector, to a Bluetooth digital device. We use these Dell PDAs because they had a number of advantages. One is that the technology became obsolete so quickly you could pick them up on eBay for really not a lot of money, but they were really chunky and solid. We'll come back to the PDA in a second. This is the kind of some insight into the disto conversion. So the disto X310 is the Leica device. We replaced the battery compartment with a USB charging lead. The main board from the thing was that the original version actually tapped into some test pads on the PCB, and it scraped the data going to and from the LCD display to get the laser distance, because the really hard thing to build yourself is a laser measure. And so we used the off-the-shelf laser measure, scraped the data off the LCD test pads, and got those into a daughter board that went on. The second version, there wasn't room for a daughter board, so the app designed a completely custom PCB that replaced the entire internals, apart from the laser measure part, the laser unit of the Leica. So this custom mainboard had a battery soldered onto it, and to get that 1/2 degree accuracy of compass required an environment that was very low magnetic interference. And so these were medically, they were non-magnetic lithium-ion batteries, lithium polymer batteries, made by medical devices company in the US. And we would get these in, solder them onto the board. That's the Leica board. You can see there's a couple of big solder blobs that are where the battery connectors join. So you have to desolder that, take out the bolt, take off all the ribbon cables, and solder in this replacement board. And this has got, I think it's an STM32 chip on it, a microcontroller. It's got a Bluetooth module, and it had the IMU components, I think 3 separate ones for the 3 axes, and it would have a complex calibration process where you would effectively, if you imagine the laser pointer being my hand, you would take a measurement of the same route with it rotated through 4 kind of like a barrel roll around the axis of the laser, and with that calibration data you do that for all the corners and faces of a cube from a point, and with all that data the calibration routine could then give you the accurate compass, clino and distance measure no matter which way up you held it. So as a caver you could give it to what we would call a hairy arse caver, and they would blunder through the cave and put it on the station and press the button, and it would measure the data whichever way up they were holding it, and that would then Bluetooth into the PDA. One of the great things about these PDAs was that they had this big fat external battery compartment, and you could fit a bigger aftermarket battery in there, which meant that this thing would last longer than your energy for a cave surveying trip. So you never had to worry about running out of power with the PDA. We're now moving to mobile phones, Android phones, because you can't get the PDAs anymore, and the modern kind of Bluetooth standards aren't supported by them, but then you have kind of battery life problems, and so you need to kind of maybe take booster packs and things to solve that. How do you keep a piece of tech like that waterproof? Otter made these OtterBox cases, which are fantastic. They have like a couple of straps on the back, so you put them on your hand and you can grip it. It's completely now waterproof, but also it's solid enough that you can lean on it. So when you're climbing up and down in the cave or crawling through, and you can stick it inside your kind of suit, and you can lie on it, and it's not going to crush the electronics. So there's the kind of the modern kit, and the Leica just goes in that soft carry case, so really it's only 2 items that you're carrying. So that's the kit. Let's have a look at what we do with the data. So coming into the PDA, this is the software package that was written for the PDA. So first of all, the numbers come in. So you can see that we number the stations, so the from station and the to station have a number. So we're going from 1.0 to 1.1, and you've got the distance, you've got the azimuth or compass bearing, and you've got the inclination. So 0.7 means very, very slightly uphill. And you can see that it's measured 3 times. So in order for the software to know that you were measuring a leg and it needed to set a new station, you would measure 3 times the same thing, and if they correspond, you know you've not messed it up, the laser hasn't missed and kind of like gone past the station or reflected off some water and given you a misreading. But also getting 3 readings would enable it to auto increment the survey station, and then it would move on to the next one. So you can see it automatically has gone to 1.1. I didn't need to kind of add a new station, and then I'm measuring not just left, right, up, down now, because I've got a laser that measures a vector and it's really easy to measure. So I'll measure everything. I'll kind of like zap around the room and get all the features, and they all come in. So the central backbone comes in. So you can see here it's kind of built up a kind of point to point. That's the plan view. But also I've got a kind of drawing interface. So as the lines come in, see here, so station 0 was just on the wall, and then I've gone to station 1, which was, I've drawn a boulder to show it was on the tip of a boulder. Makes it easy to find that station again if we're coming back to time or surveying. And then I've done my kind of splays to measure the wall distances. But we also record passage detail. I try and remember mentally to record 5 things when I'm drawing. So the walls, kind of the most obvious thing. Where do the walls go in plan view? Where does the roof and ceiling go in elevation view? So we also draw the kind of like extended cross section. I also want to know what's on the floor, what kind of passage detail. And I also, and I tend to put them on the elevation because then they don't tend to get in the way, we draw passage cross sections. So when we take those kind of left, right, up, downs, you can actually draw what does the passage look like through that. So we're recording all the same kind of information that you would record if you were drawing it on paper, but it's coming in to scale, so you're drawing to scale. And I'm just going to open up another example to show that as we move on to bigger places, and it wasn't that one, at least it was that one I wanted. Let's try that one. So here's a bit of passage that we found. We called it a sloppy inlet. You can see on the cross section that that's because it was about half full of water. So you could just about kind of do it hands and knees and kind of keep your torso out of the water. But this kind of like long sloppy crawl, and then it started to go up into some climbs. But you can actually see in the context how it fits into the whole cave system. So we're not just talking kind of like a few tens of hundreds of meters of cave here. We're now in a big cave system. And so let's switch over to the model again. So we were down round about here, a sloppy inlet. So you can see after going through that kind of crawl, it kind of grew up into something. And if I turn on passage walls to see the kind of the more 3D model. So when we started surveying this system, there was about 48 kilometres of known passage. We're now approaching the 70 kilometre mark. So, and I started working this cave system in 2006. So in a little under 20 years, we've added 20 kilometres. That's a cave that nobody had ever in the history of mankind been in before. So these are places that are unique, and you can be the first person on Earth to walk somewhere. And you know no one's been in there because you've dug the sediment out from the last kind of ice age kind of flooding events in order to get in to the new sections of passage. So we get these really nice kind of 3D models, but what do we do with our maps? So let me switch to so we want to kind of draw this up nicely, and in the old days people just used to kind of draw stuff up in programs like sort of vector drawing packages, or something like Inkscape. The problem is that as you go round one of these big cave systems surveying, eventually you sometimes kind of join up with somewhere where you kind of came in. And I'm just going to switch back to change the colour. So we can look at the colour by date. So you can see kind of like some of this survey data is from the 1970s, so it was kind of like transcribed off paper and put into the software, and it goes right up to kind of this year, where a whole new set of kind of higher level stuff was found and provided access into the depths of the system. But also we can colour by error. So an error is when we close a loop. So when a bit of cave passage kind of goes around in a loop and joins back onto itself, the ends don't always meet because you get errors in every reading and they accumulate as you go around. So this program does a least squares error reduction in the loop closure, and it moves all the stations to kind of pull it together. And you can see by the colour how good or bad a job the surveyors did as to whether there's some blunders in there and whether the error is kind of like down in the kind of 1% range, which is in noise, or whether it's up in the kind of 12%, which means somebody really ought to go back and measure it again because something went wrong. The problem if you've drawn kind of your 60 kilometres of cave beautifully up in Inkscape, and then someone closes a loop or finds a new entrance and we GPS that and it shifts everything, then that least squares kind of thing pulls the backbone of the cave to a different position to what you've drawn. So Cave has developed drawing packages that are like vector drawing packages where you attach your vector drawing to the backbone, and it produces these sorts of beautiful maps that you can see here. Now there's two problems with you're trying to solve with drawing a map. One is when two passages cross over, which one's above the other? And the other is this kind of loop closure distortion. And the way that the software handles it is you draw what are called scraps, which are short sections of passage that don't overlap. So by overlap I mean they don't cross over each other. So a scrap can be one continuous kind of bit of passage as long as it doesn't cross over itself. And that way, all the survey stations in the scrap can be adjusted to kind of distort that scrap to fit the position they are after the least squares loop closure has been done. The other thing is that because the scrap doesn't cross over itself, you know the height of the passage from the survey stations attached to it, and therefore any other scrap that overlaps it, the software knows whether it's above or below, and so it automatically can do this this kind of smooth, kind of shaded, showing the passage under or over. We can also offset, so you can see here there's a kind of big chamber which would rather obscure this area of the cave, and so we've offset it and drawn it there so that the map's more readable, but its actual true position is in this kind of black and white outline. So there's lots of kind of nice things we can do, and if we look at a more detailed section of this, drawn of a larger amount of the cave, that chamber is actually shown in place with a lot more cave. So you can generate the map in multiple ways from the same data set, which is great. Some other ways we've come up with kind of how do you actually present a kind of 70-kilometre cave system map? That's kind of that's a big sheet of paper. It's kind of impractical to print them out. So one of the things that we've done is produce these kind of map overlay tiles. So this is the cave system we were looking at in northern Spain, and you can see that as I zoom in, the cave survey is overlaid as initially the kind of 3D model, and then as we zoom in further, we actually get down to the detail. And I'm just going to jump ahead to show you a couple more things because we're nearly out of time. We can also use this kind of zoom technique to make a composite map. And here's one where I've actually put together lots of cave survey from different eras. So there's a little bit of kind of hand-drawn that never got kind of drawn up. There's this pen and ink drawing that somebody did. And then here's some of the kind of modern stuff. Join it all together and produce this kind of like, here's the full kind of, this isn't the full 70 kilometres, this was when it was about 60 kilometres cave survey. One final thing that the software can do, which is immensely powerful, is when we've got our 3D model, again, it's obviously great to be able to kind of look at the 3D model in context, but it's also really useful to be able to look at it with respect to the landscape. And so here we've overlaid a landscape, and now we can actually see kind of like how far underground are we in some of these passages. So you can see that kind of under the mountain ridges, these passages go a long way underground without actually losing a lot of height. So they kind of go in at the valleys. Turn on entrances, we can see where the entrances are. So there's an entrance in this valley down the bottom, and then we go under this big kind of mountain and it comes out, and there's more entrances in this valley over here, which is how we get into the cave. And we can see that there's some places where the cave system kind of goes up a long way and kind of breaks the surface, and sure enough there's an entrance there with, I think this pitch, just to give you an idea of scale, is just over 100 metres straight down. So you go in a short bit of distance and then there's no floor, and 100 metres down is the cave passage carries on. I think we're pretty much at time there, so thank you. I hope you found that whistle stop tour interesting on how we map caves.